This next set of videos are going to take a look at a clever trick that we can use to change a differential equation which may be difficult to solve in the world of calculus into an easier to handle equation that would be in the world of algebra, where we have many more tricks and much more familiarity. The way this works is we use this thing called a Laplace transform. And so this video is going to take a look at the question, what is a Laplace transform? So we'll start with the definition of our Laplace transform. We're going to use this notation. It's kind of a curly L with squiggly brackets around a function f of t to mean take the Laplace transform of the function. And we will define a Laplace transform as the integral from 0 to infinity of e to the negative st times f of t dt. And the solution to that integral we're going to represent with a capital letter of that same function, with now the variable will be s. And what this Laplace transform does is it converts a differential equation in t into an algebraic equation in S. We'll look at exactly how that works in future videos. For now, we're just going to look on how we actually calculate a Laplace transform. So let's take a look at a couple examples using this definition. Let's say we wanted to find the Laplace transform of maybe e to the 3t. Well, to do that, we're going to take the integral from 0 to infinity of e to the negative st times our function e to the 3t dt. And we can simplify that a little bit by adding those exponents, giving us e to the negative st plus 3t dt. And a little more simplifying, I'm going to factor out that t. Actually, let's factor it out as a negative so that the sign is positive, s minus 3 dt. And that's going to make the actual integration a little easier. Now we're ready to integrate this. When we integrate, we get e to the negative t times s minus 3 divided by, or times negative 1 over the s minus 3. And we're going to integrate that from 0 to infinity. Now, technically, when we integrate to infinity, what we should do is integrate from 0 to b, and then take the limit as b goes to infinity and evaluate that limit. But I think we can intuitively see what's happening. As our t approaches infinity, we end up with a negative huge number in our exponent. And e to a negative huge number is 0, and 0 times anything is 0. So we'll subtract, and then we'll plug the 0 into our exponent of t, which is going to give us a negative, makes it a positive, 1 over s minus 3, times e to the 0, which is 1. So this comes out to be 1 over s minus 3. And so what we found is the Laplace transform of e to the 3t is 1 over s minus 3. Let's try another example. This example is going to be a little more involved. We're going to find the Laplace transform of the sine of 3t. Using our definition, then, this is going to equal the integral from 0 to infinity of e to the negative st times our function, which is the sine of 3t dt. The integral is a little more involved, but we know how to handle this. We can use integration by parts, where u is equal to the sine of 3t. And dv is equal to e to the negative st dt. That way, our du is going to be equal to 3 cosine of 3t dt. And v can be equal to negative 1 over s e to the negative st. Putting that together, we have u times v, which is negative 1 over s e to the negative st times the sine of 3t, minus the integral of v du. Notice the 3 and the negative 1 over s, at least in terms of t, are constants. So I'm going to pull those out, which makes it a positive 3 over s times the integral of e to the negative st cosine of 3t dt. Well, we're going to use integration by parts again in much the same way. The cosine of 3t is our u. dv is equal to e to the negative st dt. That makes our du negative 3 sine of 3t dt. And v becomes negative 1 over s e to the negative st. The front part all stays the same. It's not actually part of the integral. 1 over s e to the negative st times the sine of 3t plus 3 over s times, and now our integral, u times v, is negative 1 over s e to the negative st times the cosine of 3t minus the integral of v du. And again, we have constants out front. Negative times a negative is a positive. 3 over s times e to the negative st times the sine of 3t dt. And what I want to notice is this integral I ended up with is in fact exactly the original integral we were trying to solve for. So if I say this is equal to my original integral, I'm going to use capital I just to save some space to represent my integral that I'm solving for. We can then move all the i's to one side and solve for what I that integral is. But first, we have to do a little distributing. So when I do that, we get negative 1 over s e to the negative st sine of 3t minus 3 over s squared e to the negative st times the cosine of 3t minus 9 over s squared times our integral equals the integral. Moving the integral to both sides, then, we have negative 1 over s e to the negative st sine of 3t minus 3 over s squared e to the negative st cosine of 3t equals I plus the 9 over s squared I. And if we factor out the I, we get 1 plus 9 over s squared. And if we get a common denominator on that, it would be s squared plus 9 over s squared. And so to clear that fraction, we're going to multiply by the reciprocal, which gives us s squared over s squared plus 9 times our 1 over s negative e to the negative st times the sine of 3t minus 3 over s squared e to the negative st times the cosine of 3t is equal to our integral. But we're not done yet. Remember, we were integrating this from 0 to infinity. So let's do that. Intuitively, you can see when we plug the infinity in, we're going to end up with, again, each term having an e to the negative infinity, which becomes 0, which is really nice. So plugging infinity in just gives us 0 minus. When we plug 0 in, we have s squared over s squared plus 9 times the sine of 0 goes to 0. The cosine of 0 is 1. E to the 0 is 1, so we have a negative 3 over s squared. And so with a little bit of simplifying, the negative and times the negative is a positive. The s squareds divide out, and we get 3 over s squared plus 9 is the Laplace transform for the sine of 3t. Now, as you can see, doing this algebra can get really ugly, especially if we have to do it for more complex or many functions. And so usually what we end up doing is we identify some common Laplace transforms and organize them in some type of table of values. For example, I could make a list of common functions we work with, and then correlate them with the Laplace transforms of those functions. And I'm going to make this 2 columns just to save on space. Normally this would be just one long table, but I want to try and get it all on one screen. So the first function we're going to look at is the Laplace transform of 1. The Laplace transform of 1 is 1 over s. Then we might be interested in the Laplace transform of t. Well, the Laplace transform of t turns out to be 1 over s squared. In fact, you might be noticing a pattern. If we took t to any exponent, we would say the Laplace transform is n factorial over s to the n plus 1. Another common one that we often see, in fact, we did an example of it, is e to the at, where a is some constant. Turns out the Laplace transform there is 1 over s minus a. Another common Laplace transform we have to calculate is the sine of some constant times t, or the cosine of some constant times t. And you'll recognize with the sine of the constant times t, the form is going to end up being the constant over s squared plus the constant squared. And with the cosine, it turns out to be s over s squared plus the constant squared. And so these tables can help us, along with one important property, that the Laplace transform of a constant times a function plus a constant times another function turns out to be, we can distribute that Laplace transform through and pull the constants out, giving us a times the Laplace transform of the first function plus b times the Laplace transform of the second function. And if there were many functions, we could continue that on. For example, if I was calculating the Laplace transform of 4e to the negative 2t minus 5 cosine of 4t plus 7t cubed minus 6, I can take the Laplace transforms of the functions individually with the constants popped out front. In other words, 4 times the Laplace transform of e to the negative 2t minus 5 times the Laplace transform of the cosine of 4t plus 7 times the Laplace transform of t cubed minus 6 times the Laplace transform of just a 1. And then we can use the table for each of these individual Laplace transforms. We have 4 times. Our e to the negative 2t becomes 1 over s minus the exponent. A negative 2 makes it a plus 2. Minus 5 times, with cosine, we take s over s squared plus our constant squared. 4 squared is 16. Plus 7 times the Laplace transform of t cubed. Using our table up above, that's 3 factorial over s to the 3 plus 1. Minus 6 times the Laplace transform of 1, which is 1 over s. And then we can quickly simplify these as 4 over s plus 2 minus 5s over s squared plus 16 plus 3 factorial is 6 times 7 is 42 over s to the 4th minus 6 over s. And we just calculated the Laplace transform of that ugly function. All right, now it's your turn to practice. Practice finding Laplace transforms by the definition, and also practice finding Laplace transforms from a table of transforms. Good luck to you as you practice.